Hello, and welcome to General Astronomy Lecture 8, a tour of the solar system. So, our ancestors long ago recognized the motions of the planets through the sky, but it has only been a few hundred years since we learned that the Earth is also a planet that orbits the Sun. Even then, we knew little about the other planets until the advent of large telescopes. More recently, however, the dawn of space exploration has brought us far greater understanding of other worlds. We've lived in this solar system all along, but only now are we getting to know it. In this lecture, we'll explore our solar system like newcomers to the neighborhood. We'll begin by discussing what we hope to learn by studying the solar system, and in the process take a brief tour of major features of the Sun and the planets. We'll also explore the major patterns that we observe in the solar system. Finally, we'll discuss the use of spacecraft to explore the solar system, examining how we are coming to learn so much about our neighborhoods. So, what you'll see in these first several slides is just us looking at each main object in our solar system, with a couple stats for each one, while I discuss some various features. Then for the second half of the lecture, we'll talk about the general properties among all of the planets, which we call comparative planetology. So let's get into it. Well, we'll start with our most prominent feature of the solar system and the central focus, as we've learned now in the heliocentric model of the solar system, the Sun. The Sun is by far the largest and brightest object in our solar system. It contains more than 99.8% of the solar system's total mass. So even though we have all these planets and the asteroid belt and all those rocky objects out there, the Sun still makes up 99.8% of all mass in our solar system. So that makes it nearly 1,000 times as massive as anything else in our solar system combined. The Sun's surface may look solid in photographs, but it is actually a rolling sea of hot hydrogen and helium gas, where the temperature is on average 5,800 degrees Kelvin. Now, Kelvin is a temperature scale that we're going to use pretty much throughout the entire course. I'll occasionally reference the degrees in Fahrenheit, which we're used to in the United States, but just note that understanding at least relative scales in Kelvin is very important. So the surface temperature of the Sun is about 5,800 Kelvin or 10,000 degrees Fahrenheit. The surface is speckled with sunspots that appear dark in photographs, but only because they are slightly cooler than their surroundings. Solar storms sometimes send streams of hot gas that soar far above the surface. In fact, you can kind of see a little bit of that down here, which is a very large feature. Even though it looks fairly small compared to the rest of the Sun, you could fit entire Earths inside of these loops. The Sun is gaseous throughout, and the temperature and pressure both increase with depth. The source of the Sun's energy lies deep within its core, where the temperature and pressure is high enough such that the Sun is a nuclear fusion power plant. Each second, fusion transforms about 600 million tons of the Sun's hydrogen into 596 million tons of helium. The missing 4 million tons becomes energy in accordance with the famous equation from Einstein, E equals mc squared. It turns out that mass can be converted into energy. Despite converting 4 million tons of mass to energy each second, the Sun contains so much hydrogen that it has already shown steadily for almost 5 billion years, and will continue to do so for another 5 billion years. The Sun is the most influential object in our solar system. Its gravity governs the orbits of planets. Its heat is the primary influence of the temperatures of the planetary surfaces and atmospheres. It is the source of virtually all light in our solar system. Planets and moons, they only shine by virtue of sunlight that they reflect. They don't give off their own light. In addition, charged particles flowing outward from the Sun, which we call the solar wind, helps to shape planetary magnetic fields and influences our atmospheres. Nevertheless, we can understand almost all the present characteristics of the planets without knowing much more about the Sun than we have just discussed. So let's continue our tour to the first planet, that which is closest to the Sun, Mercury. Mercury is the innermost planet of our solar system, and the smallest of the 8 official planets. It is a desolate, cratered world with no active volcanoes, no wind, no rain, and no life. Because there is virtually no air to scatter sunlight or color the sky, you would be able to see stars even in the daytime if you were to stand on Mercury's surface with your back toward the sun. You might expect Mercury to be very hot because of its relative closeness to the sun, but in fact it is a world of both hot and cold extremes. Tidal forces from the sun have forced Mercury into an unusual rotational pattern. Its 58.6 day rotation period means that it rotates exactly 3 times for every 2 of its 87.9 day orbits of the sun. This combination of rotation and orbit gives Mercury day and nights that last for about 3 Earth months each. Daytime temperatures can reach 425 degrees Celsius, which is nearly as hot coals, and at night or in shadows, maybe along a crater wall, the temperatures can fall below minus 150 degrees Celsius as well, far colder than Antarctica in the winter. Mercury's surface is heavily cratered, much like the surface of our moon, but it also shows evidence of past geological activity, such as plains created by ancient lava flows and tall, steep cliffs that run hundreds of miles in length. These cliffs may be wrinkles from an episode of planetary shrinking early in Mercury's history. Mercury's high density, which can be calculated from its mass and volume, indicates that it has a very large iron core. Perhaps it once suffered a huge impact that blasted away its outer layers. Now, this is just our tour of the solar system. We're actually going to learn all of these different things in detail in our coming lectures, but just some very interesting points and kind of a hint at what we're going to be learning about. All right, so we'll move on now to the next planet, the one that is closest in size to the Earth, and that is Venus. Venus, which is the second planet from the Sun, is nearly identical in size to Earth. Before the era of spacecraft visits, Venus stood out largely for its strange rotation. It rotates on its axis very slowly and in the opposite direction of the Earth. So days and nights are very long, and the sun rises in the west and sets in the east, instead of the opposite here on Earth. Its surface is completely hidden from view by dense clouds, so we know very little, we knew very little about its surface until a few decades ago, when spacecraft were able to map Venus with cloud-penetrating radar, discovering mountains, valleys, craters, and extensive evidence of past volcanic activity. We now know that an extreme greenhouse effect bakes Venus's surface to an incredible 470 degrees Celsius, which is about 880 degrees Fahrenheit, trapping heat so effectively that nighttime offers no relief. Day and night, Venus is hotter than a pizza oven, and the thick atmosphere bears down on the surface with a pressure that's equivalent to nearly a kilometer or 0.6 miles below the ocean's surface here on Earth. So, I mean, imagine swimming more than half a mile underwater. That's what the pressure feels like if you were to theoretically stand on the surface of Venus. But far from being a beautiful sister planet to Earth, Venus resembles a traditional view of hell. I mean, it's got the molten landscapes, really intense pressure. We'll learn about its atmosphere in a bit, but it's not pretty either. So, you know, at first, before we were able to use these cloud-penetrating radars, it looked like another Earth almost to us. But we learned that it's quite the opposite. So the fact that Venus and Earth are so similar in size and in composition, but so different in surface conditions, suggests that Venus could teach us an important lesson. In particular, Venus's greenhouse effect is caused by carbon dioxide, the same gas that is primarily responsible for the climate change that we're experiencing here on Earth. Perhaps further study of Venus may help us better understand and solve some of the problems that we face here at home today. So, speaking of home, the next planet in our journey is Earth. Beyond Venus, we encounter our home planet Earth, the only known oasis of life in our solar system thus far. Earth is also the only planet in our solar system with oxygen to breathe, ozone to shield the surface from deadly solar radiation, and abundant surface water to nurture life. temperatures are pleasant because Earth's atmosphere contains just enough carbon dioxide and water vapor to maintain a moderate greenhouse effect. Despite Earth's relatively small size, its beauty is striking. Blue oceans nearly 3/4 of the surface, they cover that much of the surface, broken by the continental landmasses and scattered islands. The polar caps are white and covered with snow and ice. We have white clouds that are scattered above our surface, and at night the glow of artificial lights reveals the presence of an intelligent civilization. I mean, relatively speaking, of course. Earth is the first planet on our tour with a moon. The moon is surprisingly large compared to Earth, although it is not the largest moon in the solar system. Almost all other moons are much smaller relative to the planets that they orbit. The leading hypothesis holds that the moon formed as a result of a giant impact early in Earth's history. Again, something that we will learn about fairly soon in our coming lectures. All right, so next up is Mars, a planet that we may be traveling to ourselves very, very soon. So this is the last of the 4 inner planets of our solar system. Mars is larger than Mercury and the Moon, but it's only about half Earth's size and diameter. Its mass is about 10% that of Earth. Mars has 2 tiny moons, Phobos and Deimos, which probably were once asteroids that were captured into the Martian orbit early in the solar system's history. Mars is a world of wonders, with ancient volcanoes that dwarf the largest mountains on Earth, a great canyon that runs nearly 1/5 of the way around the planet, and polar caps made of frozen carbon dioxide, or what we call dry ice, and water. Although Mars is frozen today, the presence of dried-up riverbeds, rock-strewn floodplains, and minerals that form only when water is present offers clear evidence that Mars had at least some warm and wet periods in the past. Major flows of liquid water probably ceased about 3 billion years ago, but some liquid water could still persist underground and perhaps flow on the surface on occasion. And in fact, we have seen direct visual evidence of this in recent years. Mars's surface looks almost Earth-like, but you wouldn't want to visit it without a spacesuit. The air pressure is far less than that on top of Mount Everest here on Earth. The temperature is usually well below freezing, the trace amounts of oxygen would not be enough to breathe, and the lack of an atmospheric ozone would leave you exposed to deadly ultraviolet radiation from the sun. So, although it is probably the closest to being an Earth-like planet for us, it's still not perfect. So you would definitely need a spacesuit to visit. And I believe right now, NASA just started training some astronauts in the deserts here on Earth so that they can test how humans handle environments that are similar to Mars. So we're getting ready for a trip there, and we'll see how that goes. It should happen within the next decade, I believe. All right, so we finished our tour of the terrestrial planets, or the inner 4 planets. Now we reach the Jovian worlds, the outer 4 planets. And the first that we come to is Jupiter, the largest in our solar system. To reach the orbit of Jupiter from Mars, we must traverse a distance that is more than double the total distance from the Sun to Mars, passing through the asteroid belt along the way. Upon our arrival, we find a planet that is much larger than any we have seen so far. Jupiter is so different from the planets in the inner solar system that we must adopt an entirely new mental image of the term planet. Its mass is more than 300 times that of Earth, and its volume is more than 1,000 times that of Earth. Its most famous feature, a long-lived storm called the Great Red Spot, is itself large enough to swallow 2 or 3 Earths. So this little spot here, we can fit 2 or 3 Earths just inside that little spot. So that gives you kind of an idea of how big this planet actually is. Like the Sun, Jupiter is made primarily of hydrogen and helium and has no solid surface. If we plunge deep into Jupiter, the increasing gas pressure would crush us long before we ever reached its core. Jupiter reigns over dozens of moons and a thin set of rings that are too faint for most photographs to pick up. Most of the moons are very small, but 4 are large enough that we'd call them planets or dwarf planets if they orbited the Sun independently. These 4 moons, known as Io, Europa, Ganymede, and Callisto are often called the Galilean moons because Galileo discovered them. These are those four moons that, if you recall back in our history lesson, that Galileo first discovered and was one of the reasons why the heliocentric model became the dominant model in astronomy, because he saw for the first time something orbiting a planet and not Earth. I lost where I was in my train of thought here. So those four moons, which we call the Galilean moons, because Galileo discovered them, they also display varied and interesting geology. For example, Io is the most volcanically active world in the entire solar system. Europa has an icy crust that we believe hides a subsurface ocean of liquid water, which makes it a promising place to search for life. And then Ganymede and Callisto may also have subsurface oceans, and their surfaces have many features that remain mysterious to us today. Next in line is Saturn. The journey from Jupiter to Saturn is a long one. Saturn orbits nearly twice as far from the Sun as Jupiter. Saturn, which is the second largest planet in our solar system, is only slightly smaller than Jupiter in diameter, but its lower density makes it considerably less massive, about 1/3 the mass of Jupiter. And in fact, Saturn is so, it's not dense to the point where, technically if you were able to find a giant body of water, its density is less than that of water. So, in theory, if it were to hold together, it would technically be able to float on water. So it is, like Jupiter, made mostly of hydrogen and helium, and also has no solid surface. Saturn is famous for its spectacular rings, as you can see in the photo. Although all four of the giant outer planets have rings, only Saturn's can be seen easily. The rings look solid from a distance, but in reality they are made of countless small particles, each of which orbits Saturn like a tiny moon. These particles of rock and ice range in size from dust grains to city blocks. We are rapidly learning more about Saturn and its rings through observations made by the Cassini spacecraft, which has orbited the planet since 2004. Cassini has also taught us more about Saturn's moons, and has revealed that at least two are geologically active today. Enceladus, which has ice fountains spraying out from its southern hemisphere, again, another place that is good to search for life, and Titan, the only moon in the solar system with a thick atmosphere. Saturn and its moons are so far from the Sun that Titan's surface temperature is a frigid minus 180 degrees Celsius, making it far too cold for any liquid water to exist. However, studies by Cassini spacecraft and its Huygens probe, which landed on Titan in 2005, have revealed a remarkably Earth-like landscape, including an erosion-covered surface with riverbeds and lakes, except that the features are shaped by extremely cold liquid methane or ethane rather than liquid water. Next up is Uranus. It's another long journey to the next stop on our tour, as Uranus lies twice as far from the Sun as Saturn. Uranus is much smaller than either Jupiter or Saturn, but still much larger than the Earth. It is made largely of hydrogen, helium, and hydrogen compounds such as water, which is H2O, ammonia, which is NH3, and methane, CH4. Methane gas gives Uranus its pale blue-green color. Like the other giants of the outer solar system, Uranus lacks any solid surface. More than 24 moons orbit Uranus, along with a set of rings somewhat similar to those of Saturn, but much darker and more difficult to see. The entire Uranus system, which consists of the planet, the rings, and the moons that orbit it, is tipped on its side compared to the rest of the planets. This extreme axis tilt may be the result of a cataclysmic collision that Uranus suffered as it was forming, and it gives Uranus the most extreme seasonal variations of any planet in our solar system. If you lived on a platform floating in Uranus's atmosphere near its north pole, you'd have continuous daylight for half of each orbit, or 42 years. Then, after a very gradual sunset, you'd enter into a 42-year-long night. So as you can imagine, that probably wouldn't be too pleasant. All right, next and our last technical planet is Neptune. The journey from the orbit of Uranus to the orbit of Neptune is the longest yet in our tour, calling attention to the vast emptiness of the outer solar system. Nevertheless, Neptune looks like a twin of Uranus, although it is more strikingly blue. It is slightly smaller than Uranus in size, but a higher density makes it slightly more massive, even though the two planets share a very similar composition. Like Uranus, Neptune has been visited only by the Voyager 2 spacecraft. Neptune has rings and numerous moons, the largest of which, called Triton, is larger than Pluto and is one of the most fascinating moons in the solar system. Triton's icy surface has features that appear to be somewhat like geysers, although they spew nitrogen gas rather than water into the sky. Even more surprisingly, Triton is the only large moon in the solar system that orbits its planet backward, that is, in a direction opposite to the direction in which Neptune rotates. This backward motion, or orbit, makes it a near certainty that Triton was once orbiting the Sun independently before it became captured within Neptune's gravitational pull and started to orbit it. Alright, so that is our 8 planets, but we do still have some other stuff out there, that being the dwarf planets. So we conclude our tour at Pluto, which reigned for some 75 years as the 9th planet in our solar system. However, the 2005 discovery of the slightly larger ERIS, and the fact that dozens of other recently discovered objects are not much smaller than Pluto and ERIS, this led scientists to reconsider the definition of a planet. The result was that we now consider Pluto and ERIS to be dwarf planets, too small to qualify as official planets, but large enough to be round in shape. Several other solar system objects also qualify as dwarf planets, including the largest asteroid of the asteroid belt named Ceres. Pluto and ERIS belong to a collection of thousands of icy objects that orbited the Sun beyond Neptune, making up what we call the Kuiper belt. As you can see, the Kuiper belt, it's actually, do I have that on here? No, I don't have it. So if you have the text, you can look at the figure in the text. We'll get to this in a little bit. But the Kuiper belt is much like the asteroid belt, except that it is farther from the Sun and composed of comet-like objects rather than rocky objects. Pluto's characteristics help us think about what it would be like to visit the distant realms. Pluto's average distance from the Sun lies as far beyond Neptune as Neptune lies beyond Uranus, making Pluto extremely cold and quite dark even in the daytime. From Pluto, the Sun would be little more than a bright light among the stars. Pluto's largest moon, Charon, is locked together in synchronous rotation, so Charon would dominate the sky on one side of Pluto but never be seen from the other side. Okay, so that is our tour. So what we're going to do now is look at general properties throughout all of the planets and discuss them compared to one another. So in science, it's often best, when we're talking about planetary studies at least, to compare them to other things that we see. Just looking up the properties of a single planet isn't that useful. So from here, I present to you just 2 tables. This is the first of 2, of the properties of the planets. Now, I'm not going to sit here and list off every single number here. This is mostly for reference. But if you want to pause or use this for reference for anything else, it's a great place to find out some of the properties of these planets. So this table here shows the first 4 planets, the inner or terrestrial planets, and it gives you all sorts of information, such as how far away they are from the Sun, how long it takes for them to orbit, what angle that their orbit is relative to the ecliptic, and all that sorts of stuff. The mass, the density, the diameter, and so on. So that is the table for the inner planets, and then on the next slide, same thing but for the outer planets. So this could be a great resource for you, and if you're interested, you can take a look at some of these. I will be asking a few questions, though, in the next few slides, so you might want to come back to these once I ask them. So let's begin with those. First one, calculation check. Which of the planets has an orbital path that is most nearly a perfect circle in shape? So if you remember, way back in our discussion on eccentricity when we talked about elliptical orbits when discussing Kepler's work, we saw that eccentricity ranges from 0 to 1, where 0 is a circle and 1 is a really big ellipse. So go back into those tables and look for whatever planet has a perfect or nearly a perfect circle in shape, which means, well, think about the eccentricity. I'll leave it there. So take a moment, go back to the table and think about it, pause your video, and return when you're ready or stuck. Alright, well, as I mentioned, the shape of a planet's orbit is given by the value of its eccentricity. The closer this value is to 0, the closer the orbit's shape is to that of a perfect circle. According to the tables, the orbit of Venus has the eccentricity closest to 0, a value of 0.007, making it the most circle-like planet of all planetary orbits. So let's just go back. We're looking for eccentricity, which is this fourth row here. And if you notice, for the inner planets, Venus does have the smallest number. Let's just check the outer planets though. And nothing is quite that small. So, yep, Venus is indeed the planet with the most circle-like orbit. Okay, next one. A planet's average density can be estimated by measuring its size and how much the planet's gravity deflects a nearby spacecraft's path. If the density of rocks recovered from a planet's surface is lower than the average planet's density, what can one infer about the density of the planet's core? So take a moment, think about that, pause your video, and return when ready. Alright, well, you're taking rocks from the surface, so if the density is lower in that sample than the average density of the entire planet, that should tell you that the core must have a higher density than the rest of the planet. And this is not surprising. This is something we will learn about. It's called differentiation. But gravity causes materials of greater density to sink toward the center of a planet. Much like if you drop a stone in a lake. The stone is more dense, so it falls to the bottom. Well, when planets are forming, they're entirely molten. So the heavier, or denser, the denser material will sink toward the core of that planet in much the same way. So that gives you an idea. All right, one more calculation here. This one might require a little bit of math. If Earth's diameter is 12,756 kilometers and Saturn's is 120,536 kilometers, how many Earths could we fit across the diameter of Saturn? So try to calculate that and pause your video to return when you're ready. All right, well, we have a large planet and a small planet. Take the two numbers, take the largest and divide it by the smallest, and we find that we would get roughly 9.5 Earths to fit across Saturn's diameter. And for comparison as well, if you look at Jupiter, we could actually fit 11 Earths across Jupiter. And here's an image showing you that to actual scale. So this is 11 Earths fitting across just the diameter of Jupiter. So it gives you a sense of scale, at least for our own planets. All right, let's get into our comparative planetology now. Galileo's telescopic observations began a new era in astronomy in which the sun, moon, and planets could be studied for the first time as worlds, rather than as merely points of light in the sky. Since that time, we have studied these worlds in different ways. Sometimes we study them individually, for example when we map the geography of Mars or the atmospheric structure of Jupiter. Other times, we compare the worlds to one another, seeking to understand their similarities and differences. This latter approach is what we call comparative planetology. Note that astronomers use the term planetology broadly to include moons, asteroids, and comets, as well as planets. The essence of comparative planetology lies in the idea that we can learn more about an individual world, including our own Earth, by studying it in the context of other objects in our solar system. It is much like learning more about a person by getting to know his or her family, friends, and culture. The comparative planetology approach should also benefit you as a student by helping you stay focused on processes rather than on a collection of facts. We now know so many individual facts about the worlds of our solar system and others that even planetary scientists have trouble keeping track of them all. I mean, even me, I studied astronomy for so long. There's no way that I or anyone I know has the capacity to just remember all of these facts about different things. You typically specialize in one area, otherwise you look at the broader ideas here. So by concentrating on the processes that shape the planets rather than these collections of facts, you can gain a deeper understanding of how the planets, including our own world, actually work. So, a planet falls naturally into one of two categories according to the size of its orbit. The orbits of the four inner planets, which are Mercury, Venus, Earth, and Mars, are crowded in close to the Sun. In contrast, the orbits of the four outer planets, which are Jupiter, Saturn, Uranus, and Neptune, are widely spaced and distant from the Sun. So this is one way we can group planets into one of two categories, inner planets and outer planets. And they are separated by the asteroid belt. You'll also notice several clear patterns of motion along the larger bodies of our solar system, and these are very important. So, for example, all planetary orbits are nearly circular and lie nearly in the same plane. So you can see they're almost all completely circular. There are small variations in the eccentricity, but they're all close to being a circle. Also, they're all very closely aligned in the same plane. In other words, they're not angled far from the average horizontal. So you can see here, if you look at a cutout view or the side view of the orbits, most of them lie in the same plane, with only small variations in the inclination. Furthermore, all planets orbit the Sun in the same direction, that is, counterclockwise as viewed from above the Earth's North Pole. Most planets also rotate in the same direction in which they orbit, with fairly small axis tilts. The Sun also rotates in this direction. And last but not least, most of the solar system's large moons exhibit similar properties, in that their orbits around their planets are all in the same direction, such as, and they all rotate in the same direction as well. So we have a very clear pattern of motion in our solar system, namely that it's circular, they orbit the Sun counterclockwise, and rotate in that same direction. So we consider these orderly patterns together as the first major feature of our solar system. Our theory of solar system formation, which we'll talk about next, explains these patterns as a consequence of processes that occurred during the early stages of the birth of our solar system. So, our brief planetary tour showed that the four inner planets are all quite different from the four outer planets. We say that these two groups represent two distinct planetary classes, terrestrial and Jovian. The terrestrial planets, which literally translates to Earth-like. Terrestrial means Earth-like. They are the four planets of the inner solar system, that is, Mercury, Venus, Earth, and Mars. These planets are relatively small and dense, with rocky surfaces and an abundance of metals in their core. They have few moons, if any, and no rings. We count our moon as a fifth terrestrial world because its history has been shaped by the same processes that have shaped the terrestrial planets. So, this graphic here shows you our four terrestrial planets. Next, then, are the Jovian planets. The Jovian planets, where Jovian means Jupiter-like, are the four large planets of the outer solar system, Jupiter, Saturn, Uranus, and Neptune. The Jovian planets are much larger in size and lower in average density than the terrestrial planets, and they also have rings and many moons. They lack solid surfaces and are made mostly of hydrogen, helium, and hydrogen compounds, again, such as water, ammonia, and methane. Because these substances are gases under earthly conditions, the Jovian planets are sometimes called gas giants. And so this table is just, again, another one of those references. It summarizes the general properties comparing the two types of planets. So terrestrial planets are, by general terms, smaller and less massive. They have a higher density because they're made mostly of rocks and metals instead of hydrogen and helium gases. They have solid surfaces, few if any moons and no rings, and they lie close together and close to the Sun. So this is, again, another good reference if you need it. Okay, so we haven't talked about this yet, but there are other objects out there in the solar system other than just the Sun and the planets. So we have lots of other small objects flying around. So we'll begin our discussion on that with the asteroid belt. So in addition to those 8 planets, many smaller objects do orbit the Sun. These objects fall into 3 categories: asteroids, trans-Neptunian objects, and comets. Asteroids, which are also often called minor planets, are rocky bodies that orbit the Sun, much like planets, but they are much smaller. Most known asteroids are found within the asteroid belt, which lies between the orbit of Mars and Jupiter at about 2 to 3.5 astronomical units. In other words, 2 to 3.5 times as far away from the Sun as we are on Earth. The asteroid shown in this image, which is called 433 ERIS, is only 33 kilometers or 21 miles long and 8 miles wide, about the same size as the island of Manhattan. Because ERIS is so small, its gravity is too weak to have pulled it into a spherical shape, so you see this kind of oblong shape instead. One common misconception about asteroids is that they are the remnants of an ancient planet that somehow broke apart or exploded, like the fictional planet Krypton in the comic book Adventures of Superman. In fact, the combined mass of all the asteroids is much less than the mass of the Moon, and they were probably never part of any planet-sized body. The early solar system is thought to have been filled with asteroid-like objects, most of which were incorporated into the planets. The leftover objects that missed out on the process of making up present-day planets are these asteroids. So that's the first type of these 3 objects. The next are the Kuiper belt objects, or the trans-Neptunian objects. So the outer solar system hosts what we now know as trans-Neptunian objects. These are small bodies whose orbits lie beyond the orbit of Neptune, so even further than our furthest planet. Just as most asteroids lie in the asteroid belt, most of these objects orbit within a band called the Kuiper belt that extends anywhere from 30 to 50 astronomical units away. The first of these to be discovered was Pluto in 1930 with a diameter of 2,274 kilometers. This is larger than any asteroid but smaller than any planet or any of the moons listed in the tables that we've shown. If you want to reference a table on these satellites or moons, you can look at table 7.2 of our text if you have it. The orbit of Pluto has a greater semi-major axis, is more steeply inclined to the ecliptic. It actually lies at 17 degrees, so you can see it's not really in the same plane as the other planets, and it has a greater eccentricity, 0.25, so it's much more eccentric than any of the other planets. In fact, Pluto's non-circular orbit sometimes takes it nearer to the Sun than Neptune, but happily the orbits of Neptune and Pluto are such that they will never collide. Pluto's density is only 2,000 kilograms per meter cubed, or about the same as Neptune's moon Triton. Hence, its composition is thought to be a mixture of about 70% rock and 30% ice. Since 1992, astronomers have discovered more than 900 other trans-Neptunian objects, and they're still discovering more each year. And note, it's hard to find them because they are very far away and small, and they don't give off lots of light or anything either. Like asteroids, the vast majority of them orbit the Sun in the same direction as the planets. A handful of these objects are also comparable in size to Pluto, and at least one, ERIS, is even larger than Pluto, as well as being in an orbit that is much larger and more steeply inclined and more eccentric, which you can see here in this giant green ellipse. Astronomers estimate that there are 35,000 or more such objects with diameters greater than 100 kilometers. If so, the combined mass of all trans-Neptunian objects is comparable to the mass of Jupiter, and is several hundred times greater than the combined mass of all of the asteroids that are found in the inner solar system. Like asteroids, trans-Neptunian objects are thought to be debris left over from the formation of the solar system. In the inner regions of the solar system, rocky fragments have been able to endure continuous exposure to the sun's heat, but any ice originally present would have evaporated. So that's why we don't really see much ice in the asteroid belt. But far from the sun, ice has survived for billions of years. Thus, debris in the solar system naturally divides into 2 families: rocky asteroids and partially icy trans-Neptunian objects, which can be arranged according to distance from the sun, just like the 2 categories of planets, which were terrestrial and Jovian. So this brings us to the last part of our discussion for this lecture, the Oort cloud. Objects in the Kuiper belt can collide if their orbits cross each other and be diverted into an elongated orbit that brings it close to the sun. Such small objects, each a combination of rock and ice, are called comets. Some comets appear to originate from locations far beyond the Kuiper belt. The source of these is thought to be a swarm of comets that forms a spherical halo around the solar system called the Oort cloud. This hypothesized halo extends to 50,000 AUs from the Sun. So note, we do say hypothesized. We actually have not detected it because it is so incredibly far away. We're talking 50,000 astronomical units. The Kuiper belt is 30 to 50, and that's already further than any of our planets. So this is, what, 1,000 times farther away? So we haven't actually had any direct proof of this, other than the fact that we do see these comets coming in every once in a while close to the Sun, where you see this very defined and general characteristic of comets. When they do get close, they start to evaporate, and you can see the dust and gas and ice coming off of them. So this was our tour of the solar system. This just gives us some general ideas as to what we're going to be seeing and talking about. Our next lecture is actually discussing the formation of our solar system. So now that we know what's out there in a general sense, we can begin to discuss how it became this way. You know, why do we have terrestrial planets nearby the Sun and Jovian planets far away? Why do we have this material left over in these weird belts? And so on. So in our next lecture, Lecture 9, we will talk about the formation of the solar system. But for now, as for always, thanks for watching and have a great day.